You are standing on the floor, and you are not thinking about why you are not falling through it. Your feet press against the ground, your body has weight, and everything feels completely ordinary. If you let your keys slip from your hand, they fall. If you jump, you come back down. Gravity in everyday life does not feel like a mystery. It feels like a background condition of existence, so reliable that it barely registers as a thought at all. You don't wake up each morning wondering whether gravity will switch on. It already has. It always has. In this familiar world, gravity behaves itself. It pulls things downward in a predictable way. It feels local, directional, almost polite. There is a down, and gravity knows exactly where it is. For centuries, this behavior fit perfectly into a simple mental model. Gravity is a force. Objects with mass reach out across space and tug on one another. The bigger the mass is, the stronger the tug. The farther apart they are, the weaker it becomes. Isaac Newton wrapped this intuition into an equation so elegant and so accurate that it still feels miraculous. With it, we could predict the motion of planets, the arc of a cannonball, the rhythm of the tides. And because it worked so well, we trusted it. We built machines, cities, and entire scientific disciplines on top of that trust. Gravity became the most domesticated of the fundamental forces. Electricity could shock you. Nuclear forces were hidden and dangerous. But gravity? Gravity was just there, quietly keeping everything in place. This is where our intuition was born, and it is a powerful one. In your mind, gravity is probably something like an invisible thread pulling you toward the center of the Earth. The Earth pulls the moon. The sun pulls the planets. Everything pulls everything else, and the universe ticks along like a well-balanced clock. Even when we imagine space, we tend to imagine it as a stage where gravity acts, not something that changes the stage itself. But that intuition was forged in a very narrow environment. It evolved and developed on the surface of a small rocky planet, at low speeds, weak gravitational fields, and short distances. It works beautifully for falling apples and orbiting moons. The trouble is that we carried this intuition with us when we started looking much farther out and much deeper in than it was ever meant to go. At first, nothing seems wrong. You can extend Newton's gravity from the Earth to the moon to the planets, and from the planets to the stars, and it still behaves. Spacecraft navigate the solar system using those same equations. Engineers send probes past Jupiter and Saturn with astonishing precision. Gravity, it seems, is still playing by the rules. So here's the unsettling question. If gravity works so well almost everywhere we look, why do physicists say it behaves strangely at cosmic scales at all? The answer begins with something so subtle that it took centuries to notice. Gravity doesn't just move objects through space. It seems to care about time as well. Imagine two identical clocks. One stays on the ground. The other is lifted slightly higher, farther from Earth's mass. According to everyday intuition, both clocks should tick at the same rate. Time is time. Gravity pulls on objects, not on seconds. But the universe disagrees. Even in Earth's relatively gentle gravitational field, clocks at different heights tick at different speeds. The difference is tiny, but it is real, measurable, and undeniable. Time itself is affected by gravity. This is not something Newton's picture can explain. A pulling force cannot slow down time. Something deeper is happening. This is the first crack in the comfortable story. The second crack comes when we stop thinking about gravity as something that acts instantly across space. Newton himself was uneasy about this. How does the Earth know that the sun is there? How does the pull travel? He had no answer, and for a long time nobody demanded one. The math worked. That was enough. But as physics matured, we learned to be suspicious of invisible influences acting instantly across vast distances. Nature, it turns out, is far more constrained than that. Information has a speed limit. Causes do not leap across the universe without delay. Gravity, if it were truly a force, would need a mechanism. And when physicists went looking for that mechanism, they found something profoundly unexpected. Gravity was not living in space, it was shaping space. Once you accept that space and time are not passive backdrops, but physical things that can stretch, bend, and warp, gravity stops being a simple pull. Mass does not reach out and grab other masses. Instead, mass changes the geometry of the universe around it. Objects move the way they do because they are following the shape of space-time itself. This idea is deeply counterintuitive, and that is the point. Our brains are very good at imagining forces. We are terrible at imagining curved geometry in 4 dimensions. So we keep trying to translate gravity back into something familiar, and every time we do, it slips through our fingers. And still, even this strange geometric gravity behaves well where we live. Around Earth, space-time is only slightly curved. The distortion is gentle, almost flat. The old Newtonian picture survives as an excellent approximation, like a shadow of a deeper truth. That's why we can ignore all of this weirdness most of the time and get on with our lives. But the universe is not mostly made of places like Earth. As you move outward in scale, gravity begins to reveal its true character. Around stars, space-time curbs more strongly. Around black holes, it becomes extreme, twisting paths of light and stretching time itself. And when you zoom out far enough, beyond stars, beyond galaxies, beyond anything that looks remotely like home, gravity does something that feels almost like a betrayal of everything we thought we knew. At the largest scales of all, gravity no longer behaves like a simple attraction between things. It becomes entangled with the expansion of space, with the history of the universe, with structures so vast that no single object can define them. Galaxies rotate in ways they shouldn't. Light bends where there seems to be nothing to bend it. The universe expands in a way that gravity alone, at least as we understand it, cannot easily explain. None of this means gravity is broken. It means our intuition is. The gravity you trust when you stand on the floor is real. It is just incomplete. It is a local, human-scale expression of something far stranger, something that only reveals its full nature when you stop thinking like a creature who evolved to throw rocks and start thinking like a universe that has been shaping itself for nearly 14 billion years. And the moment you do that, the question stops being, why is gravity so familiar? And quietly transforms into a much more unsettling one. If gravity is already this strange, just beyond our everyday experience, what else about the universe are we mistaking for simplicity simply because we have never strayed far enough to see it misbehave? When you leave the surface of the Earth, gravity does not disappear. That is one of the first great surprises. Astronauts floating inside the International Space Station are often described as being in zero gravity, but that phrase is quietly misleading. Gravity at the altitude of the space station is only slightly weaker than it is on the ground. If you could step outside and let go, you would not drift away into space. You would fall. The reason astronauts float is not because gravity is gone, but because they are falling continuously and never hitting the ground. The station, the astronauts, and everything inside are all dropping around the Earth together. Gravity is still pulling, faithfully, relentlessly, but it has been transformed from something that feels like weight into something that feels like freedom. This is where gravity begins to feel less like a downward pull and more like a subtle organizer of motion. Orbits are not places where gravity switches off. They are places where gravity is doing exactly what it always does, but the sideways motion is just right to keep the falling from ever finishing. At this scale, Newton's intuition still works beautifully. The moon falls around the Earth. The Earth falls around the sun. The planets trace out graceful paths that can be calculated centuries in advance. Gravity still looks like a force reaching across space, tugging on distant objects, keeping the cosmic dance in rhythm. And because this picture works so well across the solar system, it tempts us into a dangerous assumption that gravity is fundamentally understood, and that any weirdness we encounter later must be a detail, a correction, a footnote. But this confidence rests on a quiet coincidence. The solar system is small, slow, and gentle by cosmic standards. Space-time here is only lightly distorted. Newton's equations survive not because they are the deepest truth, but because they are a very good approximation. Push just a little harder, and the approximation begins to strain. Consider a spacecraft flying past a massive planet like Jupiter. Its trajectory bends, its speed changes, and mission planners can predict this with exquisite accuracy. But there is something odd hiding in the numbers. The spacecraft's path depends not only on where Jupiter is, but on where it was. Gravity does not act instantaneously. Changes propagate. The planet's motion subtly reshapes the gravitational influence it exerts. This is not how forces are supposed to work in our everyday intuition. We are used to pushes and pulls that happen now, not echoes of the past travelling through space. Already, gravity is hinting that it has more in common with waves and geometry than with ropes and hooks. Then there is time. As spacecraft move faster and venture deeper into gravitational fields, their clocks behave differently. Signals sent back to Earth arrive slightly off schedule. Engineers correct for this as a practical necessity, but conceptually it is astonishing. Gravity is no longer just guiding motion. It is quietly editing the flow of time itself. This should feel unsettling, because it means gravity cannot be just a force acting within time. It must be something that shapes time. And if it shapes time, it must also shape space, because space and time are inseparable once you start paying close attention. This realization doesn't arrive all at once. It creeps in through small discrepancies, subtle adjustments, technical footnotes. Newton's gravity doesn't fail catastrophically. It whispers that it is incomplete. Now imagine zooming out further, beyond planets, beyond individual stars, to entire star systems moving through the galaxy. Here, gravity becomes less personal. No single object dominates. Countless stars, clouds of gas, and dark, unseen components all contribute to the gravitational environment. Motion becomes collective rather than individual. At this scale, the idea of gravity as a simple pull between pairs of objects begins to feel awkward. Who is pulling whom? Every star is tugged in countless directions at once. The galaxy holds together not because of a few dominant forces, but because of a vast, distributed structure of gravity that no single object controls. And still, Newton's equations keep working. They shouldn't, but they do, at least approximately. This is the most deceptive part of gravity's story. It behaves well, just long enough to lull us into thinking it always will. There is a moment when studying motion at these scales when you realize something deeply strange. Gravity does not care about what you can see. It responds to mass and energy, not to brightness or familiarity. If something contributes to the structure of space-time, gravity will acknowledge it, whether your telescopes do or not. This realization sets the stage for a much larger shock later on. But even before that shock arrives, gravity is already slipping away from common sense. It is no longer something you can point to and say, that object is pulling this one. It is something more like a rule that shapes how everything moves together. And here is a question worth pausing on, because it rarely gets asked out loud. If gravity is just a force, why does it behave so differently from every other force we know? Electricity can be shielded. Magnetism can repel. Gravity does neither. It only attracts, and it cannot be blocked. Every bit of mass and energy participates, whether it wants to or not. That universality is not a coincidence. It is a clue. Gravity does not single out special objects. It treats everything the same, from photons to planets. Light bends in a gravitational field, not because it has mass, but because space-time itself is bent, and light must follow that geometry. This is an astonishing departure from the idea of forces acting on objects. It suggests that gravity is not something happening inside the universe, but something the universe is doing to itself. At human scales, this distinction barely matters. The floor still holds you up. The keys still fall. But as the scales grow larger, the distinction becomes everything. By the time you reach the size of galaxies, gravity is no longer just arranging motion. It is sculpting structure. It determines where stars can exist, how galaxies rotate, how clusters form, and how matter flows along invisible cosmic filaments. Gravity becomes the architect of the universe, working patiently over billions of years. And yet, even here, it is still behaving just well enough to keep its secrets hidden. The equations mostly work. The predictions are mostly right. The anomalies are small enough to ignore, until they aren't. There is a quiet tension building at this point in the story. Gravity has already abandoned the simple idea of being a force in the everyday sense. It has entangled itself with space and time, with motion and structure, with visibility and invisibility. And still, we are treating it as if it should behave nicely, as if the rules we learned on Earth should scale up without protest. they won't. Because the next step outward does not just stretch gravity. It exposes a profound mismatch between what gravity appears to be doing and what the visible universe can account for. And when that mismatch finally becomes impossible to ignore, gravity stops being merely strange and starts becoming mysterious in a way that challenges the foundations of cosmology itself. There is a moment in the history of physics where gravity quietly stops being familiar and becomes something else entirely. It doesn't happen with an explosion or a dramatic failure. It happens when you take all those small cracks, the time shifts, the delayed influences, the strange universality, and you decide to take them seriously instead of patching over them. Albert Einstein did exactly that, and what he found was not a better version of Newton's force. He found something that made the idea of gravity as a force feel almost childish. The key insight is deceptively simple. Imagine you are inside a closed box, floating in deep space, far from any stars or planets. The box is perfectly sealed, no windows, no outside clues. Suddenly, the box accelerates upward. You feel your feet press against the floor. Objects fall toward the bottom. If you drop your keys, they land exactly the way they would on Earth. From inside the box, there is no experiment you can perform that tells you whether you are standing on the surface of a planet or being accelerated through empty space. Gravity and acceleration feel identical. This is not a philosophical trick. It is a physical statement about reality. And once you accept it, gravity can no longer be a conventional force. Forces can be turned on and off. Acceleration can be caused by engines, but gravity seems to emerge automatically from motion itself. Einstein took this equivalence seriously and followed it to its logical conclusion. If gravity and acceleration are locally indistinguishable, then perhaps gravity is not something acting on objects at all. Perhaps it is something about the way space and time are structured. This is where intuition truly breaks. In Einstein's picture, space and time are not separate things stitched together by convenience. They form a single entity, spacetime. Events do not just happen somewhere, they happen somewhen as well. Motion through space cannot be separated from motion through time. And gravity, astonishingly, is not a pull across space-time. It is a bending of space-time itself. Mass and energy tell space-time how to curve. Curved space-time tells matter and light how to move. That sentence sounds abstract, but its implications are brutally concrete. When a planet orbits a star, it is not being tugged along by an invisible force. It is following the straightest possible path through a curved geometry. From the planet's perspective, it is moving freely, doing nothing special at all. The curvature of space-time does the work. This is why astronauts in orbit feel weightless. They are not escaping gravity. They are obeying it perfectly. They are following space-time's shape without resistance. Weight, in this picture, is not caused by gravity pulling you down. It is caused by the ground pushing you up, preventing you from following your natural path through space-time. This reversal is subtle, and it is deeply unsettling. It means that standing still on the Earth's surface is not a passive state. You are constantly being accelerated away from your natural trajectory. Freefall is the absence of force. Stillness is the illusion. Once you see gravity this way, time immediately becomes part of the story. Space-time curvature does not just affect where you go, it affects how fast you move through time. Clocks near massive objects tick more slowly because time itself is stretched by gravity. This is not because the clock is malfunctioning. Time is genuinely passing at a different rate. And this is not a theoretical curiosity. It is measured daily by satellites and atomic clocks. Your phone knows where it is because engineers correct for gravitational time dilation. Without Einstein's gravity, modern navigation would quietly fall apart. At this point, gravity has already become strange beyond anything Newton imagined. But the real shock is how well this bizarre idea works. Einstein's equations are not gentle approximations. They predict phenomena that sound like science fiction. Black holes, gravitational waves, the bending of light by mass, the expansion of the universe itself. And every time we have tested these predictions, the universe has agreed. Light passing near massive objects curves because space-time curves. Time near black holes slows so dramatically that from a distance it appears to nearly stop. Ripples in space-time propagate outward from colliding black holes at the speed of light, carrying energy across the universe. None of this fits into the idea of gravity as a force. You cannot shield space-time. You cannot turn it off. You cannot step outside it. Gravity is not something acting within the universe. It is the behavior of the universe itself. And yet, for all this strangeness, Einstein's gravity collapses back into Newton's at human scales. The equations simplify. Curvature becomes mild. Time dilation becomes negligible. The old intuition survives as a useful lie. This is why gravity feels so trustworthy. The universe lets us get away with misunderstanding it. But this mercy has limits. Einstein's theory tells us how space-time should curve, given mass and energy. It does not tell us why space-time exists in the first place. It does not explain what space-time is made of, or whether it is fundamental or emergent. And most troubling of all, when we apply these equations to the universe as a whole, they lead us somewhere deeply uncomfortable. On cosmic scales, space-time is not just curved around objects. It is dynamic. It stretches. It evolves. It carries memory of the universe's past and constraints on its future. Gravity becomes inseparable from cosmology. This is where our everyday intuition is completely outmatched. We are used to thinking of space as a container and time as a flow. Einstein shows us that both are actors, both responsive, both shaped by the contents of the universe. Gravity is not a thing happening in space and time. It is what space and time do in response to existence. And here is the unsettling implication that often goes unnoticed. If gravity is geometry, then understanding gravity means understanding the structure of reality itself. It means that when gravity behaves strangely at large scales, it is not misbehaving. It is revealing something fundamental about the universe that our local experience has hidden from us. At small scales, space-time politely pretends to be flat. At large scales, it cannot keep up the act. The curvature accumulates, the dynamics emerge, and the universe begins to do things that no falling apple could ever prepare you for. By the time we step beyond individual stars and start asking how entire galaxies and clusters fit into this geometric picture, we are no longer just studying gravity. We are studying the architecture of space-time on the grandest possible canvas. And that is precisely where the story begins to turn from elegant to deeply puzzling. Because the geometry we infer from observation does not seem to match the matter we can actually see. Once you accept that gravity is geometry, a strange reinterpretation of motion follows almost immediately. Paths that once looked curved suddenly become straight. Orbits stop being circles forced into shape by an invisible pull and start becoming the most natural trajectories possible in a warped space-time. A planet orbiting a star is not being dragged sideways by gravity. It is moving straight ahead through space-time, doing exactly what it would do if nothing were acting on it at all. The only reason the path looks curved to us is because space-time itself is curved. The planet is innocent. The geometry is guilty. This is difficult to internalize because our brains are wired to think in terms of forces and pushes. Geometry feels passive, like a backdrop. But in Einstein's universe, geometry is active. It shapes outcomes. It dictates motion. It decides what straight even means. Imagine drawing a straight line on a flat sheet of paper. Now imagine drawing a straight line on the surface of a sphere. From a distance, that line curves. On the surface itself, it is perfectly straight. Space-time works the same way, except the curvature exists not just in space, but in time as well. And once time joins the picture, everything changes. Near massive objects, time slows down. This is not metaphorical. It is not psychological. It is physical. A clock closer to a massive body ticks more slowly than one farther away. Gravity stretches time the way it stretches space. And because motion is a path through space-time, changing time changes motion. This means that gravity is no longer something that merely redirects trajectories. It sculpts histories. Two identical clocks placed at different heights above Earth will slowly drift out of sync. The difference is tiny, fractions of a second over years, but it is real. If you ignored it, satellite navigation systems would accumulate errors of kilometers per day. The fact that your phone can locate you at all is quiet evidence that space-time is curved exactly the way Einstein said it would be. This is one of the most unsettling aspects of gravity's true nature. Its strangest effects are not confined to exotic places like black holes. They are happening all around you, all the time. The universe simply hides them well. Now push gravity harder. Imagine a much more massive object than Earth, a star, for instance. Space-time curves more deeply. Time slows more dramatically. Light itself no longer travels in straight lines as we intuitively imagine them. It bends, not because photons feel a force, but because space-time gives them no straight alternative. This bending of light is one of the most profound confirmations of geometric gravity. Light has no mass. If gravity were a force that acted only on mass, light should be immune. And yet, when starlight passes near a massive object, it curves. The universe bends information itself. At first, this bending seems subtle, almost academic. a slight deflection near the sun, a small shift in apparent position. But when you scale up to massive galaxies and clusters, the effect becomes dramatic. Entire images of distant galaxies are stretched, smeared, and duplicated. Gravity turns the universe into a funhouse mirror. And here is the crucial realization. Gravity does not care what something is made of. It does not care whether it is matter, radiation, or energy locked in fields. If it contributes to space-time structure, gravity responds. Universality is not a coincidence. It is a signature. This is why gravity resists being unified with the other forces. Electricity and magnetism act on specific charges. Nuclear forces act over tiny distances on specific particles. Gravity acts on everything. It is not selective. It is not optional. You cannot opt out of space-time. This universality becomes even more striking when we think about weight. On the surface of Earth, you feel heavy because the ground prevents you from following your natural space-time path. The floor pushes you upward, constantly accelerating you away from freefall. The sensation you call weight is resistance to gravity, not gravity itself. This flips our everyday intuition inside out. Falling is the natural state. Standing still is artificial. Once this perspective settles in, gravity starts to feel less like an interaction and more like a condition. It is not something happening to objects, it is something happening to the stage on which objects exist. And this brings us to a subtle but critical point. If gravity is geometry, then understanding gravity requires understanding the shape of space-time everywhere, not just near individual objects. Locally, space-time can look flat. Globally, it can be anything but. This distinction barely matters near Earth. Space-time curvature is weak. The universe indulges our simplicity. But as you expand your view to encompass entire star systems, galaxies and clusters, local flatness stops telling the whole story. Curvature accumulates. Geometry becomes collective. At these scales, gravity no longer feels like something sourced by individual objects. It becomes a property of the system as a whole. The shape of space-time is determined not by one mass, but by the combined energy content of vast regions of the universe. This is where Einstein's theory quietly shifts from describing motion to describing structure. Gravity is no longer just predicting where things go next. It is explaining why the universe has the large-scale shape it does. And this is where the unease begins. Because when astronomers map the motion of stars in galaxies and galaxies in clusters and clusters across the cosmos, the geometry implied by gravity does not seem to match the matter we can see. Space-time appears more curbed than visible matter alone can account for. The equations are clear. The motion is clear. The light bending is clear. What is unclear is where the necessary gravity is coming from. At this point, gravity is no longer just strange in its behavior. It is strange in its bookkeeping. The universe appears to be curving space-time as if something invisible is shaping it. And that realization marks the moment when gravity stops being merely a triumph of elegant theory and starts becoming a deep cosmological mystery, one that forces us to confront the possibility that most of the universe's structure is being governed by something we cannot see at all. As gravity grows stronger, space-time stops behaving like a gentle landscape and starts to resemble something far more extreme. Around ordinary stars, curvature is noticeable but manageable. Around collapsed stars, neutron stars and black holes, it becomes violent. Space and time twist so severely that the concepts themselves begin to lose their everyday meaning. Take a neutron star. It is the remnant of a massive star that has burned through its fuel and collapsed under its own gravity. A neutron star can pack more mass than the Sun into a sphere the size of a city. The curvature of space-time around it is intense. If you could approach one safely, which you can't, time near its surface would slow dramatically compared to time far away. Light climbing out would lose energy, stretched into redder wavelengths. Gravity here is no longer subtle, it is overwhelming. And yet, even neutron stars are only a prelude. Black holes push gravity to its logical extreme. They are not holes in space, despite the name. They are regions where space-time has curved so deeply that no path leads back out once you cross a certain boundary. That boundary, the event horizon, is not a solid surface. Nothing special happens there locally, but globally it marks the point of no return. What makes black holes so unsettling is not just their strength, but their simplicity. From the outside, a black hole is almost boring. It can be described by just a few numbers: mass, spin, and electric charge. All the complexity of the matter that formed it, every atom, every structure, every detail, is erased from the external universe. This tells us something profound about gravity. It does not preserve individuality. It does not care about composition. Under extreme conditions, gravity strips reality down to its most minimal description. Near a black hole, space-time does something that feels almost like flowing. Paths tilt inward. Futures point towards the centre. Time itself appears to lean. Once inside the event horizon, moving forward in time means moving inward. The singularity is not a place you can avoid any more than you can avoid tomorrow. This is not metaphor. In Einstein's equations, time and space literally exchange roles inside a black hole. Directions that once felt optional become mandatory. Escape becomes as impossible as travelling backward in time. These extremes reveal gravity's true nature more clearly than gentle environments ever could. Gravity is not a background condition. It is a dynamical structure that can evolve, collapse, ripple, and trap. And those ripples are real. When massive objects accelerate, especially when black holes or neutron stars orbit and collide, they disturb space-time itself. The disturbance propagates outward as gravitational waves. These are not vibrations of matter or energy moving through space. They are vibrations of space and time. When gravitational waves pass through Earth, they do not shake buildings or knock objects over. They stretch and compress space-time by tiny amounts, changing distances by less than the width of a proton. And yet, with exquisitely sensitive instruments, we can detect them. When we do, we are not seeing black holes. We are listening to space-time ring. This is a radical shift in how we observe the universe. For most of human history, astronomy meant light. Then it expanded to radio waves, X-rays, gamma rays. Now it includes gravity itself. We are directly measuring the geometry of the universe as it moves. And here is the critical point. These observations confirm Einstein's theory with astonishing precision. Black holes behave exactly as geometric gravity predicts. Gravitational waves travel at the speed of light. Spacetime responds exactly as the equations demand. At extreme scales, gravity is not mysterious in the sense of being poorly understood. It is mysterious in the sense of being deeply alien. But there is a catch. Everything described so far, black holes, neutron stars, gravitational waves, occurs in places where gravity is strong but localized. The curvature is intense but confined. Einstein's theory thrives here. Trouble begins when we shift attention away from extreme density and toward extreme size. When we stop asking how gravity behaves near very massive objects and start asking how it behaves across enormous volumes of the universe. Because gravity, as geometry, does not only respond to dense objects, it responds to all mass and energy everywhere. And when you average over galaxies, clusters, and the vast cosmic web, the curvature you infer does not match the matter you can see. Black holes are dramatic, but they are rare. Most of the universe is empty, dark, and diffuse. And yet, that emptiness seems to curve space-time far more than it should. Stars in galaxies orbit too fast. Galaxies in clusters move as if held together by invisible glue. Light bends where there appears to be nothing there to bend it. Space-time at these scales seems to be responding to something hidden. This is where gravity's story takes a sharp turn. Not because Einstein was wrong in extreme environments, but because when we apply his perfectly successful theory to the universe as a whole, the universe answers back with a puzzle. Either there is far more mass and energy than we can see, or gravity behaves differently when space-time becomes vast rather than intense. Both possibilities are unsettling, because one suggests that most of reality is invisible to us. The other suggests that even our deepest understanding of gravity may be incomplete. Black holes show us how gravity behaves when pushed to extremes of density. Galaxies will show us how gravity behaves when pushed to extremes of scale. And the lessons from those scales will not be comfortable. They will force us to confront the possibility that gravity, the force we thought we knew best, is still hiding its most important secrets in the quiet, dark spaces between the stars. When gravity first begins to feel truly wrong, it is not near black holes or neutron stars. It is in places that look calm, orderly, almost boring. Spiral galaxies, for example. Vast, majestic pinwheels of stars rotating peacefully through space. If gravity behaved the way our intuition says it should, these systems would be some of the easiest to understand. They are not. Take a galaxy like our own. Hundreds of billions of stars orbiting a common centre, bound together by gravity. From a Newtonian perspective, or even an Einsteinian one applied locally, the expectation is straightforward. Stars closer to the centre, where most of the mass is concentrated, should orbit faster. Stars farther out, feeling less gravitational pull, should slow down. Just like planets in the solar system. Just like everything your intuition has ever learned. When astronomers first measured how fast stars move in galaxies, that is exactly what they expected to see. They didn't. Instead, something astonishing appeared. Beyond the bright central regions of galaxies, where most of the visible stars and gas reside, Orbital speeds refuse to drop. Stars far from the centre move just as fast as those much closer in, sometimes faster. The rotation curves flatten out, stubbornly ignoring the rules gravity is supposed to follow. At first, this looked like a mistake. Instruments were recalibrated, measurements were repeated, different galaxies were studied. The result did not go away. Spiral galaxy after spiral galaxy told the same story. According to gravity, these galaxies should be flying apart. They aren't. This is not a small discrepancy. The outer stars are moving so quickly that if only visible matter were providing gravity, they should escape entirely. The galaxies should unravel on cosmic timescales, and yet they remain intact, stable, and ancient. This is the moment when gravity stops being quietly strange and becomes openly defiant. One reaction is to question the observations. Another is to question the galaxies. Perhaps there is more matter than we can see. Perhaps something invisible is providing the extra gravity needed to hold everything together. This idea sounds radical, and so you realize the alternative is worse. The alternative is that gravity itself behaves differently on galactic scales. At first, the invisible matter idea felt like a patch, an uncomfortable add-on. But as astronomers pushed further, the pattern deepened. Galaxy clusters showed the same problem. Individual galaxies moved too fast within clusters to be held together by visible matter alone. The clusters should disperse. They don't. Then gravitational lensing entered the story. Light from distant galaxies bends as it passes massive objects on its way to us. This bending depends only on space-time curvature. It does not care how matter shines or hides. When astronomers mapped this lensing, they found something eerie. The curvature implied by lensing was far stronger than visible matter could produce. Worse still, the curvature was sometimes displaced from the matter we could see. In some cosmic collisions, hot gas, clearly visible, slams together and slows down. The gravitational influence inferred from lensing sails straight through, barely interacting. Whatever is providing most of the gravity does not behave like ordinary matter. It does not glow. It does not collide easily. It does not announce itself. Gravity is pointing to something we cannot see. At this point, the universe seems to be insisting on a conclusion. Either most of its mass is invisible, or gravity is lying to us. Neither option is comforting. If invisible matter dominates galaxies and clusters, then everything you see, the stars, planets, nebulae, even you, is a minor embellishment on a much larger, darker structure. The luminous universe becomes a decorative frosting on a vast, unseen cake. If gravity behaves differently at large scales, then Einstein's beautiful geometric picture is incomplete. Not wrong in the places we have tested it, but insufficient for the universe as a whole. Gravity would be scale-dependent in a way no other force is. Both possibilities undermine our sense of understanding. What makes this especially unsettling is how quietly the problem emerges. There is no catastrophic failure, no equations blowing up. Gravity works perfectly well locally. It navigates spacecraft. It predicts black hole mergers. It bends light exactly as expected. It only fails when you stop looking at individual objects and start looking at collective behavior. This suggests something deeply important. Gravity may not be a purely local phenomenon. It may care about global structure, about how matter is distributed across vast distances, about the universe as a connected whole. In everyday life, gravity feels local. Your weight depends on Earth beneath your feet. In galaxies, gravity feels communal. Every star responds not just to nearby matter, but to the entire gravitational environment of the galaxy. This breaks our mental model of cause and effect. We are used to thinking that objects influence one another through direct interaction. But galactic gravity feels more like a property of the system than the sum of its parts. And this brings us to a question that is far more disturbing than it first appears. How much of reality can be invisible before we admit that our picture of gravity might be missing something fundamental? Astronomers can map where gravity is acting without knowing what is causing it. They can trace invisible structures through lensing and motion. The universe becomes legible in gravitational ink, even when it is visually dark. Gravity, it turns out, is not just a force or geometry. It is a detective. It reveals the presence of things that refuse to be seen. But gravity does not tell us what those things are. Are they new particles, drifting silently through galaxies, interacting only through gravity? Are they relics from the early universe, shaping structure without ever lighting up? Or are they a sign that gravity itself behaves differently when space-time stretches across millions of light years? At this stage, the story refuses to resolve. Gravity has led us to a fork in the road. One path suggests that most of the universe is hidden. The other suggests that our deepest theory of gravity is incomplete. And what makes this fork so unsettling is that both paths preserve gravity's strangeness. If dark matter exists, gravity remains universal, but reveals a universe dominated by the unseen. If gravity must be modified, then space-time itself behaves differently, depending on scale, hinting at a deeper layer of physics beneath Einstein's equations. Either way, gravity is no longer the comfortable, obedient phenomenon we met on the floor of our homes. It has become a cosmic whisperer, pointing insistently towards something enormous and unknown, something that only reveals itself when we dare to think on scales far larger than anything our intuition was ever built to handle. And as we follow that whisper outward, toward the largest structures in the universe, gravity will do something even stranger still. It will stop merely shaping motion and begin shaping the fate of the cosmos itself. Gravity reveals its most poetic trick when it stops moving matter and starts moving light. Light feels untouchable. It has no mass. It travels at the maximum speed allowed by the universe. In every other force we know, light is either unaffected or only indirectly involved. So for centuries, it seemed obvious that gravity should leave light alone. A force that pulls on mass should have nothing to say to something weightless. But once gravity becomes geometry, that expectation collapses. Light does not travel through space. It travels through space-time. And if space-time is curved, light has no choice but to follow that curvature. It bends not because it is pulled, but because straight itself has been redefined. This is gravitational lensing, and it is one of the most quietly astonishing phenomena in the universe. Imagine a distant galaxy sending light toward Earth. On its journey, that light passes near another massive galaxy or cluster. Space-time around the mass is curved, and the light's path bends as it moves through. To an observer on Earth, the distant galaxy appears distorted, stretched, multiplied, sometimes even wrapped into luminous arcs. The universe turns into its own optical instrument. At first, this sounds like a curiosity, something visually striking but scientifically minor. It is neither. Gravitational lensing is one of the most powerful tools in cosmology because it does something extraordinary. It lets us see gravity directly, not through motion, not through light emitted by matter, but through the shape of space-time itself. When astronomers measure lensing, they are mapping curvature. They are tracing where gravity is acting, regardless of whether anything is shining there. And again, lensing tells the same unsettling story. There is more gravity than there should be. In some cases, the effect is subtle, a slight elongation of background galaxies, a gentle shear across an image. In others, it is dramatic. Multiple images of the same galaxy appearing around a cluster like reflections in broken glass. Perfect rings of light formed when alignment is just right, revealing a cosmic symmetry that feels almost intentional. But the real shock is not the beauty, it is the mismatch. When astronomers compare where lensing says mass must be to where visible matter actually is, the two often do not line up. The gravitational landscape appears smoother, larger, and heavier than the luminous landscape would suggest. In some of the most striking observations, entire galaxy clusters collide. Hot gas slams together and slows down, glowing brightly in X-rays. Meanwhile, the gravitational influence inferred from lensing barely notices the collision. It passes straight through, as if most of the mass were made of something that does not interact, does not collide, does not light up. Gravity exposes a shadow universe. This is a turning point in our relationship with gravity. Until now, gravity has been something we infer indirectly. We drop objects, we measure orbits, we time signals. With lensing, gravity becomes visible as distortion. Space-time itself leaves fingerprints on the sky, and those fingerprints refuse to match what we see. At this stage, gravity is no longer just behaving strangely. It is accusing reality of hiding something. If you are tempted to think this is just an observational illusion, consider how independent these clues are. Galaxy rotation curves, cluster dynamics, gravitational lensing, cosmic structure formation. Different methods, different assumptions, same conclusion. There is more gravitational influence than visible matter can provide. What makes lensing especially powerful is that it does not care about motion or equilibrium. Stars might be out of balance, gas might be turbulent, but light simply follows geometry. It offers a clean probe of space-time shape, and space-time, at galactic and cluster scales, looks far more curved than it should. This forces a confrontation with two ideas we would both rather avoid. Either most of the universe's mass is invisible, interacting almost exclusively through gravity, or gravity itself changes character when applied across enormous distances. Both ideas stretch our intuition to the breaking point. Invisible matter means accepting that everything you see is a minority component of the universe, that galaxies are embedded in vast halos of something unknown, that cosmic structure is scaffolded by entities that never emit light and barely interact with the world we know. Modified gravity means something even stranger. It suggests that space-time responds differently when curvature is weak but widespread than when it is strong but localized. That gravity is not simply geometry, but geometry with hidden rules that only reveal themselves at large scales. Gravitational lensing does not choose between these explanations. It simply insists that something is wrong with the naive picture. And there is another unsettling implication that often goes unnoticed. Lensing allows us to see the universe as it really is, not just as it appears in light. It shows us that the luminous universe is a biased sample, a tracer, not the whole story. We evolved to see stars, not space-time. Our telescopes were built to collect photons, not curvature. Gravity is telling us that reality is structured around something deeper than what shines. At this point, gravity has completed a strange transformation. It began as a familiar downward pull. It became curbed space-time. It revealed invisible mass. And now, through lensing, it has turned into a cartographer, mapping a universe that refuses to show itself directly. And still, the strangest move is yet to come. Because everything so far, dark matter or modified gravity, still assumes that gravity's basic role is to pull things together, to slow motion, to build structure. But when we zoom out even further, beyond galaxies and clusters, gravity does something that no falling object, no orbit, no lens could ever prepare us for. It appears to lose. Not locally, not in small systems, but globally, on the scale of the universe itself. Space does not just curve, it expands. And that expansion is not slowing down, it is accelerating. There is a moment when gravity's story stops being about objects and starts being about the universe itself. Up to this point, gravity has been shaping motion, bending light, sculpting galaxies, and revealing hidden mass. It has always been doing something familiar in spirit, pulling things together, slowing expansion, building structure. That expectation feels almost unquestionable. Gravity attracts. That's what it does. And then cosmology delivers a shock. When astronomers first began to measure how the universe is expanding, the assumption was simple. The expansion began fast, driven by the energy of the Big Bang, and gravity has been slowing it down ever since. Every galaxy pulls on every other galaxy. Over time, the expansion should decelerate. It might slow forever. It might eventually stop. It might even reverse. That was the intuition. It was neat. It was comforting. And it was wrong. When astronomers measured distant supernovae, stellar explosions bright enough to be seen across billions of light years, they found something deeply unsettling. These explosions were dimmer than expected, further away than expected. The universe was not slowing down, it was speeding up. The expansion of space is accelerating. This is one of the most astonishing discoveries in modern science, not because it is dramatic, but because it is so deeply counterintuitive. Gravity, the force that pulls things together, seems to be losing on the largest scales of all. Or worse, it seems to be helping push things apart. This is not expansion in the ordinary sense. Galaxies are not flying through space away from one another. Space itself is stretching. New space is appearing between galaxies. And the further apart things are, the faster that separation grows. At small scales, gravity still dominates. Galaxies remain bound. Clusters remain intact. Stars continue to orbit. Your feet remain on the floor. Gravity has not changed its mind locally, but globally, something else has taken control. This forces a radical shift in perspective. The expansion of the universe is not something happening inside space-time. It is something space-time itself is doing. And gravity is no longer just responding to matter. It is entangled with the universe's overall energy content. Einstein's equations allow this. They always have. Space-time can expand or contract depending on what fills it. Matter slows expansion. Radiation slows it even more. But there is a strange possibility hidden in the mathematics, a form of energy that does not dilute as space expands, an energy of space itself. If space has energy simply by existing, then creating more space creates more energy, and that energy has a peculiar gravitational effect. Instead of pulling inward, it pushes outward. It accelerates expansion. This idea sounds almost philosophical, but the universe seems to be acting it out. The expansion accelerates not because galaxies are trying harder to escape, but because the fabric between them is becoming increasingly energetic. Gravity, at the largest scales, is no longer dominated by attraction. It is dominated by the properties of empty space. This is the moment when gravity truly stops behaving like anything in our everyday experience. There is no analogy from falling objects, no intuition from orbits, no campfire story that prepares you for the idea that nothingness itself might be the most powerful component of the cosmos. What makes this even stranger is how subtle the effect is locally, in your home, in your city, in your galaxy. Expansion is completely irrelevant. Gravity overwhelms it. Space does not stretch tables apart or pull atoms away from one another. It does not even stretch galaxies. Expansion only becomes noticeable when gravity is weak and distances are enormous. It is a large-scale phenomenon that emerges only when you step back far enough for local structures to fade into statistical patterns. This is why it took so long to discover. The universe hid its most important behavior in the places we are least equipped to notice. At this point, gravity is fractured into two personalities. Locally, it binds and builds. Globally, it seems to surrender control. The same equations describe both behaviors, but the outcome depends entirely on scale and content. And here is where the story becomes deeply unsettling. The accelerated expansion implies that most of the universe's energy is not in matter or radiation at all. It is in this strange, smooth, pervasive component associated with space itself. Whatever it is, it outweighs everything else. Stars, planets, galaxies, clusters, all of it combined is a small minority. Gravity is telling us that the universe is dominated not by things, but by something that looks like nothing. This flips our cosmic intuition completely upside down. We tend to think of the universe as a collection of objects embedded in space. Gravity is showing us that space itself may be the main actor, with matter playing a supporting role. And once again, gravity refuses to explain itself. Is this outward push a new kind of energy? A constant built into space-time? A sign that gravity behaves differently on the largest scales than Einstein ever imagined? Or is it evidence that our understanding of space-time is missing a crucial ingredient? Every option is uncomfortable. If space has intrinsic energy, then emptiness is not empty. The vacuum becomes a physical entity with gravitational consequences. If gravity must be modified at cosmic scales, then even Einstein's geometry is an approximation, incomplete in ways we are only beginning to glimpse. And if both are true, then gravity is not a single phenomenon at all, but an emergent behavior with different faces at different scales. At this point, gravity has carried us far from falling keys and orbiting moons. It has forced us to accept curbed spacetime, invisible mass, distorted light, and now accelerating expansion. Each step has widened the gap between intuition and reality. The most unsettling part is not that gravity behaves strangely at cosmic scales. It is that gravity behaves reasonably at human scales. It behaves just well enough for just long enough to convince us we understand it, until we dare to look at the universe as a whole. And when we do, gravity stops being a force, stops being geometry, and starts becoming a question about the nature of reality itself. Because whatever is driving the expansion of the universe is not just modifying gravity, it is rewriting the future. And the fate of everything, galaxies, stars, atoms, and time itself, depends on which version of gravity turns out to be the final one. At this stage, gravity has cornered us. Every path forward feels uncomfortable, and that discomfort is the point. The universe is no longer letting us hide behind approximations or intuition. It is forcing us to choose between explanations that all feel slightly wrong. One possibility is that most of the universe is made of something we cannot see. This idea has a certain brutal simplicity. Keep gravity exactly as Einstein described it. Trust the geometry. Trust the equations. If space-time is curving more than visible matter can explain, then the missing curvature must be caused by missing matter. Not exotic gravity, exotic stuff. This invisible component would not glow. It would not absorb light. It would barely interact with ordinary matter at all. It would drift through galaxies, clusters, and cosmic filaments, shaping structure silently. Galaxies would form inside vast halos of it, like lanterns suspended in fog. In this picture, gravity is innocent. It is doing exactly what it is supposed to do. We are the ones who have been staring at the wrong part of the universe. And there is something deeply humbling about this idea. It suggests that everything we have ever seen with our eyes or telescopes is just a thin, luminous trace of a much larger reality. Stars and galaxies become surface features, not foundations. But this solution comes at a cost. Despite decades of searching, we have never directly detected this invisible matter. We infer its existence through gravity alone. We map it by its effects, not its presence. It shapes galaxies, bends light, and guides cosmic structure, yet refuses to show itself in any other way. That silence is unsettling. So there is another possibility, one that feels even more radical. Perhaps gravity itself is incomplete. Perhaps Einstein's theory, as successful and beautiful as it is an approximation that breaks down when space-time becomes vast rather than intense. Perhaps gravity changes behavior when accelerations become extremely small, when curvature is spread thinly over enormous distances. In this view, there is no missing matter. The equations themselves are missing something. This idea is dangerous because it cuts deep. Einstein's gravity is not just a theory of motion, it is a theory of space-time itself. Modifying it means questioning how geometry responds to existence. It means rewriting the rules of cosmic structure. And yet, this idea has an uncomfortable appeal. The anomalies appear precisely where gravity is weakest, at the outskirts of galaxies, in the low acceleration environments of cosmic voids, in regimes far removed from the strong gravitational fields where Einstein's theory has been tested most thoroughly. It is as if gravity behaves differently when it is spread thin. This is profoundly counterintuitive. We're used to thinking that forces weaken smoothly, not that their laws change. But gravity has always been the odd one out. It already refuses to behave like other forces. It already treats space-time itself as malleable. Why should scale not matter? And then there is the most unsettling possibility of all, that both ideas are true, that there is invisible matter shaping galaxies and clusters, and that gravity itself behaves differently at cosmic scales, that space-time is responding to contents and conditions in ways we do not yet understand, that gravity is emergent rather than fundamental, a collective behavior arising from deeper physics. In this view, Einstein's equations are like the laws of fluid flow, accurate, powerful, but not fundamental. They describe how space-time behaves on average, not what it is made of. Just as water looks smooth until you examine molecules, gravity may look geometric until you probe its microscopic structure. This possibility opens a door to something even stranger. If gravity emerges from deeper laws, then space and time themselves may not be fundamental. They may arise from more basic ingredients, stitched together in ways we do not yet grasp. The universe we experience could be a large-scale illusion, a smooth surface hiding a radically different underlying reality. This is no longer just cosmology. This is a question about what existence is made of. And gravity is the thread pulling at that question. It is worth pausing here to notice something quietly extraordinary. Gravity is the weakest of the fundamental interactions. You can overcome the entire gravitational pull of Earth with a small jump. And yet, gravity dominates the universe at the largest scales. It shapes galaxies. It controls cosmic history. It decides the fate of expansion. This inversion is not accidental. Gravity accumulates. It does not cancel. It does not shield. It builds up over distance and time until its influence dwarfs everything else. This is why gravity becomes most mysterious, precisely where it becomes most important. At this point, the universe is asking us something uncomfortable. Are we prepared to accept that most of reality is invisible? Or are we prepared to accept that our understanding of space-time itself is provisional? Either answer changes how we see ourselves. If most of the universe is hidden, then our existence is perched on a narrow island of visibility. We are creatures of light, living inside a sea of darkness we barely comprehend. If gravity must be rewritten, then even our deepest physical intuitions are temporary scaffolding destined to be replaced. There is no version of this story that ends with comfort, and perhaps that is the most honest lesson gravity has to teach us. Gravity began as the force that keeps our feet on the ground. It became the geometry of space-time. It exposed invisible mass. It revealed accelerating expansion. And now it stands at the edge of explanation, pointing towards something beyond itself. The universe is not hiding these truths maliciously. It is simply vast enough, old enough, and subtle enough that the rules change as the scale changes. Our intuition, forged on a small planet in a young corner of cosmic history, was never meant to survive this journey intact. And yet, gravity has been generous. It has left us clues. The question now is whether those clues are pointing toward unseen matter, new laws of gravity, or a deeper layer of reality beneath space-time itself. Because whatever the answer turns out to be, it will not just explain why galaxies rotate the way they do, or why the universe accelerates. It will explain what kind of universe we are actually living in. And that brings us to the final, unsettling realization. Gravity does not merely describe motion, it describes destiny. Gravity brings us back to where we began, but nothing feels the same anymore. You are still standing on the floor. Your feet are still pressed against the ground. If you drop your keys, they will still fall. Gravity has not changed its behavior in any way that affects your daily life. And yet, after everything we have uncovered, it is impossible to see that simple act the same way again. What you feel as weight is not gravity pulling you down. It is the ground pushing you up, forcing you off your natural path through space-time. What you call stillness is resistance. What you call falling is freedom. Even here, in the most familiar setting imaginable, gravity has already been quietly defying intuition. And beyond this small, comfortable patch of space-time, gravity becomes something else entirely. It bends light. It slows time. It erases information. It exposes invisible structures. It governs galaxies you will never see and distances you will never cross. It sculpts a universe in which almost everything that matters is hidden from direct view. Most unsettling of all, gravity does not behave as a single simple idea. It behaves differently depending on where you look. Near Earth, it feels like a force. Near black holes, it feels like fate. Across galaxies, it feels like a shadow pointing to unseen mass. Across the universe, it feels like a question mark written into space-time itself. This is not a failure of physics. It is a reminder of scale. Our intuition evolved to survive falls of a few meters, not to comprehend curvature stretched across billions of light years. We are exquisitely tuned to a tiny gravitational regime and almost blind to everything beyond it. The universe did not design gravity to be understood by creatures like us. We are reverse engineering it from the inside, armed with mathematics, patience, and a willingness to accept that common sense is a local phenomenon. Gravity behaves strangely at cosmic scales, not because it is broken, but because we are looking at it in contexts far removed from where our instincts were forged. It is like judging the ocean by a puddle, or climate by a breeze. And yet, despite this mismatch, gravity has been astonishingly kind to us. It leaves traces. It bends light in measurable ways. It imprints patterns on the sky. It allows us to infer the invisible and reconstruct the past. Even when it confounds us, it does so consistently, honestly, leaving clues rather than chaos. There is a quiet beauty in that. Gravity may turn out to be caused by unseen matter, or it may turn out to be an emergent phenomenon arising from deeper laws that do not resemble forces or geometry at all. Space and time themselves may dissolve into something more fundamental when we finally understand gravity completely. Or perhaps gravity is telling us something even more unsettling, that the universe does not have a single, clean explanation waiting to be uncovered, but layers of description that only make sense at certain scales, each true in its own domain, none complete on their own. If that is the case, then gravity is not just a force or a law. It is a translator. It translates the microscopic into the cosmic, the local into the global, the visible into the invisible. It connects falling apples to expanding universes, without ever promising that the same story will make sense at both ends. And this may be the most important lesson of all. The universe is not obligated to be intuitive. It is only obligated to be consistent. Gravity is consistent, relentlessly so. It obeys its rules with no regard for human expectation. When those rules produce galaxies that spin too fast, light that bends too much, or space that expands too quickly, gravity is not malfunctioning, it is revealing. What feels strange is not gravity. What feels strange is discovering how narrow our original understanding was. We mistook familiarity for simplicity. We mistook reliability for completeness. We mistook a local truth for a universal one. Gravity let us do that for a long time, because near Earth the universe is gentle, but the cosmos is vast, and gravity, patient as it is, eventually shows its full face. And when it does, it tells us something humbling and profound. The universe is not built around our intuition. Our intuition is a small, temporary adaptation living inside a much larger, much stranger gravitational reality, one that has been shaping space, time, matter, and destiny since long before there were minds to wonder why things fall at all.